A 300-gram ball is traveling as a projectile through the air. At point 1, it has a speed of 14 meters per second, and at point 2, it has reached an elevation that is 6 meters below point 1, or 6 meters lower than point 1. Between points 1 and 2, air resistance does negative 5.0 joules of work on the ball. Determine the speed of the ball at point 2. I'm going to start by drawing a little diagram. So we have a ball. It's going through the air, and sometime later it's at a lower elevation than when it started. And the number is given, the difference in elevation is 6 meters. All right, so in terms of labeling things with the variables, this is going to be a conservation of energy problem with a little bit of non-conservative forces doing some work on it. So I'm going to want to label speeds and heights using subscripts of 1 and 2. So at the beginning, I'm given the beginning speed of 14 meters per second. So I will label that as V1. 14 meters per second. And H1, the starting height, I need to set my reference height, and I think a pretty good choice would be to set the height of the second point to be the reference height. So where I drew this dotted line, my reference height here is h equals 0 meters. That means that H1, where it started from, would be 6 meters. In terms of point 2, so it travels, and at point 2, the speed, v2, is what we're asked to calculate here. So I'll label that with a question mark. And h2, the height at point 2, since I've set my reference height to be right here, h2 can be 0 meters. Now, along the way, it says that air resistance did negative 5 joules of work on the ball. So I'm going to label that with W and C. I could label that with W air as well if I wanted to, but I want you to get used to the term non-conservative force. Air resistance is a non-conservative force. And the work done by that force is negative 5 joules. And finally, the mass of the ball, that's important, so I'll just write that somewhere and convert that to kilograms. Okay, so it said 300 grams, I converted that to kilograms. All right, there's my list. I listed it in a diagram. I think both are important when solving these kinds of questions. All right, now I'll go ahead and try to apply the conservation of energy formula from the previous lesson. So I'll start at the very beginning. Mechanical energy at point 1. I'm going to leave a little space here, equals mechanical energy at point 2. But they're not equal. Okay, they're not equal because of that negative 5 joules of work. And you got to know which side that goes on. It goes on the side with the starting energy. Okay, so you take your starting energy, and then you add or subtract whatever the work was to that starting energy, and that's going to equal the final energy. Okay, the mechanical energies will be broken down into kinetic and potential. Okay, so oftentimes I won't even write that first step with the ME. A lot of times I'll just go right to the U's and the K's. It's up to you. And now I'm going to cross out anything that is 0. And in this case, I believe my U2 would be 0 because my height at point 2 is 0. Okay, I think that's all that's 0. So now I'll change the K's to the formula for kinetic energy, and I'll change the U's to the formula for gravitational potential energy. So the formula for kinetic energy is half times mass times speed squared. And the formula for gravitational potential energy is mgh. Now in terms of work, the WNC, I did not change that to the formula for work because I'm given the value in joules already, -5 joules. Okay, so that's already the whole term right there. Don't need to change that into any other formula. All right, at this point we can either plug in the numbers, and calculate all out, and isolate for V2. We could rearrange it all for V2 first and then plug in the numbers. That's up to you. In this question, I'm going to just go with the plugging in numbers first method. So I'll plug in the mass and the speeds, or the first speed. So I was noticing, marking some of your stuff, that you need to be a little more careful in terms of not leaving anything out. So I've seen some solutions where they forgot to square one of the speeds, or if they forgot to put the mass in for mgh, and it's really, since there's so many things here, it's really easy to make those kinds of mistakes. So you got to be really careful. So this WNC here is -5. All right, that's filling in all the numbers. There's a lot going on there, but I'm going to calculate things out. So get my calculator ready here. So the first term is half times 0.3 times 14 squared. That's 29.4. So that's the starting kinetic energy, 29.4 joules, plus the starting gravitational, that'll be 0.3 times 9.8 times 6. That's 17.64 joules. And then the minus 5 joules of work equals, on the other side, half times 0.3, that would be 0.15, and then V2 squared. All right. The left side, I'll just calculate that out. That's 42.04. And then just finish off solving that. So divide both sides, 5.15, and then square root both sides. So after doing all that, I'm coming up with an answer of rounded to two significant figures. I'm getting 17. All right. So that's how you do this example of mechanical energy when there is work done by non-conservative forces. I'll do one more example in the next video, and then it's up to you to practice.